My name's Tim Clark. I'm the project leader of the Verney speed sailing team. We've set ourselves the challenge of setting a new world speed sailing record. This involves taking the average speed of a sailing boat over a 500-metre long course. Verney Yachts, the company, was set up purely to facilitate the speed sailing project. The V44 Albatross has been designed specifically for the task in hand to break a new speed sailing record. It has two rigid composite wing sails, one set horizontally to the surface and one set vertically. The vertical wing sail acts as a sail in the conventional sense, where the horizontal wing sail provides lift and lifts the hulls clear of the surface of the water. The boat can tack by rolling through, the wing sails roll through 90 degrees as the boat tacks, so each wing sail changes function. In other words, the vertical sail becomes the horizontal wing sail and the horizontal wing sail becomes the vertical wing sail. So at speed, the boat is literally flying above the surface of the water with just the keel and the rudder penetrating the surface of the water. And this enables a very high degree of active control. The skipper has control of the boat in all three axes, controlling the height of the boat above the surface and roll and yaw. We're looking for the V44 to achieve 65 knots, which is about 120 kilometres an hour, just under 20% faster than the current record. The biggest challenges that we face with designing the composite structure of the boat is the fact that the aerodynamic and hydrodynamic design of the boat is very sensitive to the way the structure behaves under load. In other words, we need to get an understanding of the coupling effects that we have between the structural design and the fluid design of the boat. We need to be able to use realistic simulation to basically converge on a design, testing a lot of different approaches. So we need it to be able to allow us to quickly and effectively visualize the effect of taking different approaches, particularly at the earlier stages of the design process. We also need a high degree of automation with the co-simulation of FEA and CFD. We chose Abaqus Unified FEA because it's given us everything that we need throughout the whole design process, from enabling us to quickly converge onto a design within the concept design stage by using it like a design tool, enabling us to quickly visualize the effects of taking different concept approaches, all the way through to the detailed tuning of composite structures towards the end of the detailed design stage. The key features of Abaqus are the co-simulation engine. It helps us to automate the process of coupling FEA with CFD. It's a very important part of the project to help us to understand how the behaviour of the structure of the boat influences the aerodynamic and hydrodynamic design of the boat. The technical requirements that really benefit us are the extensive functionality within the interaction module within Abaqus. Specifically at the earlier stages of the design, it's enabled us to quickly and effectively visualize the effects of taking different approaches without the simulations becoming too lengthy or too costly computationally. We're using SolidWorks for 3D modelling. We find that this is very user-friendly, very effective and efficient 3D modelling package. We're using the associative interface between SolidWorks and Abaqus to help bring in the geometry. The advantages of realistic simulation for a project like ours is that from the very beginning we've decided to take a very engineered approach. To date, speed sailing projects have tended to take a much more experimental approach, where they're designing in a lot of flexibility, a lot of adjustability in the layout, and they're making pretty heavy modifications to the boat as they progress. So we're looking to carry out a lot more simulation before we actually build the boat itself.